Hritik Goel. I'm here to present our work on the topic exploiting site information for intelligent and reconfigurable PHY experiments on LTE transceivers. So here is a problem setup. Resource allocation in wireless network via multi-arm banded algorithms has been studied widely in literature. So in the conventional setup, feedback signals such as signal to interference noise ratio, rank indicator, channel quality indicator, and precoder matrix indicator are sent by the user over the uplink channel to the transmitter. Transmitter will make use of such feedback signals to select the best channel and configure the corresponding PHY parameters. For example, SNR is used to select the modulation coding scheme. RI and PMI are used to select the transmission mode and the precoder matrix for the corresponding MIMO mode. But from the below figure, we can see that the transmitter at Pico base station can sense the interference information from the neighboring base stations, and we can make use of such interference to have better decision making. So we have referred such interference as measurable interference, and will use it as side information in our work. So our work is focused on using such side information available at the transmitter along with conventional feedback signals to have high performance gains at the receiver or the mobile user equipment. So apart from measurable interference, there exists non-measurable interference. So how much is the impact of such non-measurable interference? We will try to address the issue in our work. So here is a proposed solution. There exists strong correlation between the interference at the transmitter and the bear and throughput at the receiver. For example, high interference at the transmitter implies poor PHY performance at receiver and vice versa. So UCB can exploit the side information which is assumed to be known to the transmitter to select the best channel for transmission. So we have adapted the UCB algorithm with side information, that is UCB WSI, for realistic LTE setup based on MIMO OFDM. So since we have assumed that only the side information is known at the transmitter, and we don't have any additional assumptions regarding the feedback signals, so our solution is compatible with the LT standard. It supports link adaptation and adaptive MIMO. At the end, we will see that our proposed solution outperforms the conventional RL algorithms in terms of BR and throughput. Just to mention, we haven't compared our proposed solution with the Thompson sampling because it is not clear how to incorporate side information in Thompson sampling. The below figure shows the incorporation of our RL algorithm in the transmitter chain of the LT5 setup. Suppose base station wants to communicate data to the user equipment, so the transmitter PHY chain of the base station will select the channel and configure the corresponding PHY parameters for the selected channel, and the data will be sent to the user equipment. So the receiver PHY chain will receive the channel, will receive the data, and the corresponding feedback signals such as PMI, RI, and CQI are estimated at a receiver. So these feedback signals are communicated over the uplink channel to the transmitter. So the decision-making block situated at the transmitter chain will take SINR as a feedback and select the best channel for the transmission of the next frame. And this process will iterate for each and every frame. So here is the pseudo algorithm. So K here denotes the number of channels. So initially each channel is selected 4 number of times to have so that the variance of each and every channel is well defined. Further, the UCB index of each and every channel is calculated in each time slot, and uh, the channel with highest UCB index is selected. Then after the transmission is over, the SNR feedback and the side information is observed at the transmitter, and the corresponding parameters of the selected channel, such as mean and variance, are re-estimated. And this process will iterate for each and every time slot. Simulation parameters. So this table shows the simulation parameters that we have used in our simulation and are in accordance with the LT standard. Moving over to result section. So we have compared here the performance of UCB WSI algorithm with the conventional RL algorithms. So the plot here shows the different channel combinations of the flat fitting low mobility profiles. The channel combination vary on the basis of mean SNR values. From the plot, we can see that the UCB WSI algorithm outperforms the conventional RL algorithms in terms of BRN throughput for all the channel combinations. Here we have taken three different channel profiles: flat fitting low mobility, extended pedestrian A, and extended typical urban. Just few points to mention. We have compared here our proposed solution only with UCP algorithm. Also, we haven't shown here the BR metric just to maintain the clarity of the plots, and the two plots differ on the basis of channel combinations. So from the plots, we can infer that the UCP-WC algorithm performs better as compared to the UCP algorithm in all the channel profiles. Here we will see the effect of variance in side information for the case of FLM channel profile. So what will happen in the case of high variance inside information as compared to low variance? So from the plots we can see that the low variance case performs better as compared to the high variance case for all the channel combinations. This suggests that our proposed solution provide performance gains even when the side information is erroneous at the transmitter. It also shows that the high variance in the side information implies performance degradation or poor phi performance at the receiver, and such side information uh, and we need to have better learning of such side information in our proposed solution. This will be an interesting case. Here we will see what will happen in the case when measurable interference is insignificant as compared to non-measurable interference. So from the plot, we can see that the proposed solution outperforms the UCB algorithm in terms of BRN throughput. In such cases also, this is similar to the multi-arm banded algorithm case, the conventional MAB case. It might be due to the better exploitation approach of the UCBWS algorithm and tighter confidence bounds. Also, the side information is exploited to have smaller channel variances. Up till now, we have assumed that the mean of side information is known at the transmitter, or we have prior knowledge of such information. But what will happen in case when such information is unknown at the transmitter or absent? So this will be an interesting future work. Thank you.